Okay. So in this project, we were given an electric motor rotating at 50 radian per second to drive a saw blade in a lumber mill. The saw blade must stay horizontal and complete a full back and forth motion in 10 seconds. The main goal is to design a mechanism that converts the motor's rotational motion into the required reciprocating motion and analyze the saw blade kinematics using simulation software. Going through, we will explain about the design's ideas, which we provide two design to choose from, and then we will explain about our final design chosen, and then we will also explain about the theoretical calculation about the design we choose. After that, we will use simulation to explain and test the accuracy of our theoretical calculation. And finally, we will conclude this presentation.
Assalamualaikum. My name is Nashul. For my part, I will be explaining about the design and the calculations. Our first design was to utilize the Scotch-York mechanism design, but after further considerations, unfortunately, we had to scrap the idea and finalize that the slider crank mechanism as the most valid design. This is because it has high lateral thrust and wear, where it is in constant broad area contact with the sides of its carriage slot, and this creates a significant side thrust and friction, leading to rapid wear of the yoke and guide surfaces, especially at high speeds or under high loads. Due to its pure sinus and also due to its pure sinusoidal motion, the Scotch yoke has higher peak acceleration at the ends of the stroke than the slider crank. This creates a greater inertial forces than and requiring a more robust structure and increasing stress on the components. We chose the slider crank mechanism as our design because, due to its proven efficiency in converting rotational input into controlled reciprocating linear motion, its primary advantages, which are a simple, robust architecture with minimal moving parts to ensure a high reliability and ease of maintenance. Furthermore, it is well documented that behavior allows for predictable performance and optimization of stroke length and timing. Most importantly, the geometry of the mechanism minimizes lateral strain and frictional resistance within the system, leading to an efficient power transmission and reduced wear. This combination of functional simplicity, analytical predictability, and widespread industrial validation makes it an optimal solution for the stated problem. As for the theoretical calculation, by using the kinetics formula and equation that we have learned, we have chosen two instances of angles where the crank will be situated, which are at 90 and 360 degrees. The aim and objective of the calculations is to find the velocity and accelerations of each joint at the aforementioned instances, with the assumptions that the effects of friction, cutting forces, and other external factors are negligible.
The forward cutting stroke occurs at lower speed than the return stroke due to angular configuration of the crank. This creates a quick return mechanism which is beneficial for cutting operations. The slower forward stroke allows sufficient time and force for effective cutting, while the faster return stroke reduces idle time, thereby improving overall operational efficiency. The velocity time and acceleration time results confirm that the saw blade completes one full reciprocating cycle in exactly 10 seconds, meeting the design requirement. Although the motor runs at 50 rads per second, the transmission and speed reduction system successfully reduced the crank speed to approximately 0.6 to 8 rad per second, enabling one full crank revolution per cycle and producing the required reciprocating motion. The velocity profile is non-sinusoidal, which is expected for the slider crank mechanism. This deviation from simple harmonic motion occurs due to the finite length finite length of the connecting rod. The motion behavior is governed by the L/R ratio. A smaller ratio increases asymmetry in velocity and acceleration, while a larger ratio results in motion closer to sinusoidal. The chosen L/R ratio achieves a balanced trade-off, providing subtle motion characteristic while keeping the mechanism compact and practical.
Okay, so finally we come to the conclusion which a slider crank mechanism was successfully designed and chosen to convert rotational motion into horizontal reciprocating motion of the saw blade within the required 10-second cycle. GIM software was used to stimulate and analyze the mechanism, and the result confirmed that the design meets the specified kinematic requirements, and this project highlights the effective application of the kinematics principle in the practical mechanism design. That is all from us. Thank you.